Good afternoon. My name is Paul West. I'm the Reservoir Monitoring Source Sales Director for Magseis Fairfield. I'm going to be giving you a talk today on high-resolution 3D seismic, the next generation. In that talk, we're going to be looking at the excellent data quality achieved with ultra-high-resolution 3D seismic, comparing it to ultra-high-resolution 2D seismic, and then looking at the uplift that can be provided by the use of the next generation, which is extended high resolution or XHR 3D seismic. So first of all, a little bit about Magseis Fairfield. We consist of 4 complementary business segments. The first of these is data acquisition. During our history, we have acquired over 90 ocean bottom node surveys from the Gulf of Mexico through to the Arabian Gulf. We also have 5 years of experience of acquiring P-cable or UHR 3D data. In addition, we have a segment that looks after reservoir monitoring source. And there we provide portable sources for any range of activities that you like, from VSP to DAS, but most particularly for permanent reservoir monitoring, where we have experience in the North Sea and as far as the Caspian. More recently, we've entered the renewables market, taking our hydrocarbons experience and applying it to wind farm de-risking, both for turbine placements and turbine foundations, and also for cable routing. Also in carbon capture, we look at storage mapping and monitoring, and last but not least, deep sea minerals. In addition to these segments, we also lease and sell nodes. So as I mentioned, Magseis Fairfield have been involved in UHR 3D really from its commercial inception in 2011. Right, we've acquired significant quantities of both multi-client and third-party data from 2011 through to 2015. And to date, we have recorded still more than 50% of the 3D UHR data that exists worldwide. So let's take a look at some of that data. Here we see a conventional 3D survey from the Barents Sea offshore Norway. And what we're looking at here is some polygonal faulting, which is down around about 100 meters below the sea floor. And I think you will agree it's actually quite difficult to see what's going on here. This is that same area acquired using UHR 3D data. And I think you'll agree it's an incomparable result in terms of its resolution and detail that you can see. So in this next few slides, we're going to take a look at the difference between 2D UHR and 3D UHR. And in fact, what we're looking at here is a 2D UHR line. If you look at the schematic in the bottom of the slide here, you can see that line is shown in red. Sometime later, that was overlaid with a 3D seismic survey. And in our next slide, we're going to look at a slice through that 3D volume, exactly the same location as this 2D line. So what are we looking at here? So the red box that we see up at the top there is really highlighting the sea floor down to about 100 meters below the sea floor. And about 70 meters, you can see there's a long straight event happening there, and that's a glacial unconformity. Now above that, you've got various geological features going on, but it's very, very difficult to see what they are. There's a couple of arrows there that I'll draw your attention to because we want to look at the corresponding position on the 3D slice and see how they differ. Down below the glacial unconformity, you can see again that there's some action going on down there. It looks like faulting. It's quite difficult to make out. We'll look at that again in the next slide. So I'm now going to move forwards to a slice through the 3D volume. It's in that exact same area. Now look at those 2 arrows up above the glacial unconformity, and all of a sudden what was a total mess now comes into focus, and you can actually see clearly what the geology is. Again below that same unconformity, you can now see that the hint of those faults have crystallized into very well defined faults, and that's actually the polygonal faulting that we looked at in that previous time slice. Moving on, now once again we're looking at a 3D seismic volume in that same area, and you can see that that glacial unconformity is there yet again, highlighted with a red line through it. Down below it you can see the polygonal faulting, and up above it you can see that they had issues in that area with glacial lineation, in other words iceberg scars. If we look over at the structure map generated from that 3D volume on the right hand side, you can see iceberg plough marks and also ridges taking place, and that's effectively a structure model that's going down, between sort of 60 and 70 meters below the sea surface. So you've got a very good 3D image of what's going on. Reality is, if you're acquiring this with 2D, not only would you have a less precise image, as we saw on those preceding slides, but also you may well move a drill location or a jack-up barge location in order to miss a feature, and you end up putting it into another feature because you haven't highlighted that with your 2D approach. So as we've seen, standard P cable or UHR can acquire some very, very good data, and data which is certainly better than data that can be acquired using 2D UHR. So how can that data be improved upon? So I think we need to understand a little bit about how P cable is acquired, how that data is acquired, to understand what can be done to improve for a next generation of extended high resolution data. So the first thing to note is that typically it was towed very shallow, between 1 and 3 meters in tow depth. Now that made it very susceptible to weather, both from a signal to noise perspective, but also from a robustness perspective. You're tying quite a complicated spread through the wave tops. Secondly, the sources used for P cable were almost an add-on in general to the recording system. At Magseis Fairfield, as you saw in my initial slides, we're experts in source, and we applied that technology to our P cable solution to come up with extended high resolution. Last but not least, obviously positioning on something that acquires at into such small bins is important, and that's very difficult when in-water acoustics don't work, and in-water acoustics in 1 to 3 meters don't work. You have to tow rather deeper in order to make that happen. So at Magseis Fairfield, we set about looking at how we could improve P cable and take it to a whole new generation of solution. In the process, we realized that by using different combinations of sources and combining them with different combinations of receivers, that we could actually focus the system for very specific targets, and it's not a case of one size fits all. So the first of those was XHR infrastructure, which is aimed fair and square at the wind farm industry, where they're interested in sub-meter boulders potentially down to 100 meters of depth, both for cable routings and for putting in foundations of wind turbines. Also has applications in oil field infrastructure, and that uses sparkers combined with your receiver technology. The second, and which is perhaps a wider application to normal site investigation, will be XR imaging, right? Where we're really looking at geohazard investigation from 0 down to below 1,000 meters below the seabed. Again, that can be focused by using different types of guns, etc. That's useful for geotechnical and fault investigation, also for carbon storage, mapping and monitoring, shallow oil and gas reservoir imaging, and last but not least, 4D applications. So let's take a look at these applications in a bit more detail. The first of these is XHR 3D and 4D imaging. And if you recall, this is really replacing geohazard, looking from the sea surface really down to medium depth, but we can focus it on the shallower by using different arrays of guns and different lengths of cable. Perhaps the most notable feature to look at when comparing it to standard P cable approach is that we're now towing rather deeper, certainly deeper than 10 meters. What that's doing is it's moving our cables out of the wave action and into a quieter environment from a signal to noise perspective, but also an environment where the complex spread is not going to be interfered with by waves. That deeper tow also allows us to use in-water acoustics to position the cables. So now for the first time we've got a very accurate handle on where those cables are. The second part of the equation is the source, and really we've taken what typically was used for P cable acquisition, which is a 3 to 4 octave source. We've taken that and we've extended it to provide a 6 to 7 octave source using a distributed source array, and you can see the characteristics of that down in the bottom right of this slide. That provides you with enhanced resolution at the high frequency end of it, and then true amplitudes for inversion at the low frequency end of it. If you look at the frequency spectra there, you can see how the XHR frequency spectra extends beyond that of a more standard industry approach. The second application we'll look at is XHR 3D infrastructure. If you recall, this is where you're trying to detect boulders in the very near surface, really for cable routings for wind farms, but any activity that boulders are going to impact in the near surface, both in the wind farm industry but also in the hydrocarbons industry. So here, again, depending on water depth, you're generally towing between 8 and 16 streamers. As with the XHR imaging, we're actually towing deep, below 10 meters, taking us out of the weather window. And here, instead of using air guns, we're actually using a series of sparkers, which are being towed with really pretty much a zero offset from the front of the cables. And those sparkers are dithered in the way they're acquired. So again, you end up with very small bins. From this, you'll get a very high frequency data set from a reflection perspective, but also this approach allows you to use a diffraction approach to your imaging, basically using a reverse time operator over a large aperture for sub-bin detection. That enables you to see in the near surface boulders as small as 30 to 50 centimeters. Of course, an issue that you can get with high frequency sparker sources is that the energy from those sources dissipates fairly quickly as it goes down through the surface of the Earth. And so it may be that you would want to have an approach that would give you very high resolution near surface data, but also give you reflection data to a deeper depth. And you can, as we can see here, you can combine both air gun source and sparker source in order to give you those two data types in a single pass. So this allows you to have boulder detection in the shallow, but also provides you with some deeper imaging as well. Magseis Fairfield are very well known for their portable and transportable, but also modular systems. And that's been applied both to their node surveys, to our permanent reservoir monitoring portable sources, and it was natural that that should be applied to our approach to extended high resolution 3D seismic. What we're looking at here is a series of standard 20-foot containers into which our equipment is fitted. Those containers can be put onto any vessel that has sufficient deck space and bunk space anywhere in the world. And what that means is that you can take the system and acquire a survey, let's say in the North Sea, and a few weeks later we can be acquiring a survey in the Gulf of Mexico without having to have sailed across an expensive source vessel or whatever. We can use PSVs of convenience in the location where the survey takes place. Back deck requirements are a little bit over 200 square meters, which is a fairly small PSV, and you really need bunk space for between 10 and 12 people, depending on the particular operation. From a source perspective, we can, as we've discussed, use air guns, and air guns will require a compressor. You can see that a compressor with the exhaust stack coming out of it on this vessel. If, however, we're requiring using the sparker, such as the one shown here at the bottom right, that container would be removed and replaced with a generator for the sparker source. The actual cable side, the receiver side of the operation is manufactured by a company called CMAP. It's actually they're C-Link cables. They're extremely modular. They come in various lengths, and you can plug them together in any combination or number of streamers, or frankly, if you want to, just one long streamer. Right? It's not new technology, it's proven technology. It's a new system to us. And the front end recording side of it is a CMAP 3840 recording system that gives you continuous recording, and you can output data in pretty well any format which is acceptable in the industry. So we've looked at the system and the changes that we've made to it in terms of a P cable UHR 3D approach. We've compared it to 2D, a 2D approach. Let's now just look at the operational advantages of the XHR 3D system. The first of these is the deep tow, and that improves our tolerance to weather, both from a signal to noise or geophysical perspective, but also from a robustness and our ability to operate in considerably worse weather conditions than you would be looking at operating with a UHR shallow tow system. The short cables of the system provide excellent maneuverability. So if you're working in an area which has either got shallow water, or an area which has got obstructions, such as wind farms or oilfield infrastructure, the maneuverability that having such a short cable provides is a very valuable commodity. Again, the shallow water operations, because the cable's so short, you can get into rather shallower water than you can with a longer streamer cable. And lastly, on the short cable side of things, it allows for operations in strong currents. Scalability of the system and its modularity allows for tailored solutions, whether you're looking for sub-meter boulders in the very near surface, down to geology, down to 200-300 meters or a kilometer and beyond. Lastly, and something that we've not mentioned at this point, is while we've concentrated on XHR, there's no reason that you cannot record additional measurements from the vessel, such as magnetometer or side scan sonar, etc., at the same time as you're acquiring your XHR data set. In other words, acquiring as much data as possible in a single pass. Well, I hope very much that this presentation has been of interest to you. If you do have any questions, I'd be very happy to try and answer them for you now. If I can't answer them, then I will certainly take the question away with me and come back to you. Just to remind you, my name is Paul West, and my email address is shown down there at the bottom left of this slide. Thank you very much.